I have a three-dimensional vector space here with a pair of vectors v1 and v2 inside of it. In the last video, we considered what scaling a vector by a constant and adding two vectors would mean in various vector spaces. In this video, we're going to consider expressions such as the one you see in the top left corner, where we scale one vector by a constant, scale another vector by a constant, and add the result together to get a third vector. The question is, what vectors in this vector space can be written as such a sum, including these particular two vectors? To think about this deeper, let's think about what we mean by scaling a vector. I went over this in the last video, but just to make a more visual explanation of it, when we scale a vector by a constant, we keep the vector pointing in the same direction, but we change its length. When we make that constant negative, that means that the vector points in the opposite direction of the original vector. When we make that number positive, the vector points in the same direction as the original vector with a length that depends on the magnitude of that coefficient. So one sum we could consider is 1.5 times v1 plus minus 0.8 times v2. So we rescale v1 by a factor of 1.5, and we rescale v2 by minus 0.8, which includes turning it in the opposite direction. We also moved the green vector so that its tail is placed at the head of the blue vector. Then the sum is just represented by the yellow vector, which points from the tail of the blue vector to the head of the green vector. We leave a point at the head of the yellow vector to represent that result. Another example, minus 1.2 v1 plus 1.1 v2. Again, we rescale the vectors and put them tail to head and find the yellow vector as the result. We leave a point there. We do it for one more example that we will show and use the same procedure to represent the sum. We draw the yellow vector and we leave a point there. Now this is three examples of different sums we could get from different combinations of coefficients C1 and C2. We want to consider all possible sums of this form with different coefficients C1 and C2. So we randomly sample pairs of C1 and C2 and represent the sum with points just as we did. Now, what possible vectors can be reached with a sum like this? Can they all? I think you can see that the answer is they cannot all be reached. These vectors only give us a plane of possible results. Why do the results lie in a plane? What would it take to make a sum like this be able to map out the entire three-dimensional space? These are the kinds of questions I'm going to address in this video, so stay tuned. A sum of the form that we just discussed is called a linear combination, and it's very important. So it's a sum over capital N vectors of a coefficient times each vector. In the animation I just showed you, we had C1 V1 plus C2 V2, and that's where we ended. But if we have some number of n vectors larger than 2, then it would go on until Cn Vn, like so. Now, imagine that these vectors v1, v2, vn are fixed. Then we can talk about the span of that set. When I write vi in curly brackets with these subscripts and superscripts, it means the set of vectors v1, v2, all the way up to vn. And the span of that set of vectors is all linear combinations of the form shown above. In other words, in the expression shown here, just select every possible combination of values C1, C2, and Cn up all the way up to Cn, and that full set of all of the possible combinations of values of C1 all the way through Cn will give you the full set of linear combinations, which is the span of these vectors v1, 2, 3, all the way up to n. Another topic we're going to care about is called linear independence. Given a set of vectors, just like the one we discussed, a vector u is linearly independent of the set if we cannot write u as a linear combination over the vectors in that set. We often will be curious of whether the particular vectors in this set are linearly independent of one another. So what that looks like is consider one of these vectors Vn for n in 1 to capital N. Vn is linearly independent if it can't be written as a linear combination over the other vectors. So for I not equal to lowercase n, but summing over the rest of the vectors, that this equality cannot be true for any combination of c's. If Vn is linearly independent of the others for all n in the range of vectors in the original set, then the set is said to be linearly independent. Now, consider a linearly independent set of the form I've written many times now. What linear combinations of these vectors give the zero vector? In other words, what are the solutions for the c coefficients in this equation? Well, it should be clear to you that there is a solution where c1 equals c2 equals all of the other c's equals 0. So if you just set all of these coefficients to 0, you're going to multiply each vector by 0, and you get nothing for each term, and you get the 0 vector as a result. Now, are there any other solutions? Well, let's assume that there is a solution where one of the c's is not equal to 0, at least one of them. So we have an equation c1 times v1 plus c2 times v2 all the way up to cn times vn. Let's say that c lowercase n does not equal 0, where lowercase n can be any of these values. If that's the case, we can solve for the vector vn by adding all of the terms to one side and then dividing by cn. And since cn isn't 0, by assumption, we can do that freely. So we would end up with an expression of the form, well, first we'd get cn times vn is equal to, and then we'd get minus all of the other terms in the sum. So this is I not equal to n of that same sum. Right? I just did algebra there. And then dividing by cn gives us a solution for vn. And I'm going to just distribute that division into the sum. Ci over Cn times Vi. Well, what we have here is a linear combination of the vectors other than Vn, where the coefficients in this case are minus Ci over Cn. And we're saying that this vector Vn can be written as that linear combination. Well, that means that Vn is not linearly independent, which is a contradiction. So that proves that you cannot have any solution where any of the Cn's are not equal to 0. Otherwise, you reach the contradictory conclusion that that vector had to have been not linearly independent, which was against the assumption. So if you have linearly independent vectors, the only solution to an equation like this is this one right here, that all of the coefficients are equal to 0. In other words, the 0 vector can only be represented by a linear combination where the coefficients are all equal to 0. It can be insightful to understand the concept of linear independence in the context of polynomials. Recall from the last video, polynomials are a vector space. So the space of all polynomial functions, which can be written as C0 plus C1 times x plus C2 times x squared. And a particular polynomial function is said to be the same as another polynomial function if and only if those functions are the exact same for all values of x. So each possible polynomial function is a vector in the space of all possible polynomial functions. Now, I want to know which polynomials give exactly 0, which would be a function that is 0 for all x. Can we achieve that function with coefficients that are not necessarily equal to 0? You probably are assuming the answer is no, but I will show it anyway. Just to link it up with the other example, x squared here can be thought of as a vector v2. X can be thought of as a vector v1. And here there's a 1 hiding, which can be thought of as a vector v0. A small difference is that in the other example, I began the counting at 1, and here I'm beginning it at 0. But that is simply a syntactical difference, and the overall statements are still going to apply. So I think intuitively you might be able to see that the only way to get a polynomial that is exactly 0 for all values of x is to set all of the coefficients equal to 0, but I'm going to go through it anyway just to make sure it's clear. So if C2 is not equal to 0, you know that this function will have a value that changes as x changes. And it'll change in a particular way with a changing slope. Let's say we take that and we want to assume that we have a non-zero coefficient, C2, and we want to see if we can select C0 and C1 just such that it'll cancel the C2 term perfectly. You should be able to see that that's not possible. The C0 and C1 terms only give a function with a constant slope, whereas the C2 term gives a term with a changing slope. A function with a constant slope cannot cancel a function with a changing slope. And therefore, the C0 and C1 terms cannot perfectly cancel the C2 term for all values of x. Therefore, C2 has to be 0. Now moving over to the C1 term, C1 is going to give a term, a part of the function that changes linearly with x. Now, if we make C1 not equal to 0, that means the value of that term in the function is going to be changing as we change x. Now, the C0 term is only going to be a constant, so that's not going to be changing with x. So it would be impossible to choose the C0 term in just the right way to cancel the C1 term for all x, because the C1 term is changing as a function of x, while the C0 term is not able to do that. And therefore, the C1 term is equal to 0 as well. And then lastly, we just have C0. So we have P of x is equal to C0. That doesn't depend on x at all. So it's just a question of whether that value is 0 or not. If it's not 0, then it's not the 0 function. If it is 0, then it is. So the only option is for C0 to be equal to 0 if we want to get a polynomial that is equal to 0 for all x. So this shows that the only way for a polynomial to give the 0 vector is if C0 equals C1 equals C2 equals 0. And that shows that 1x and x squared can be thought of as linearly independent vectors. All right, now we're going to think about how many different linearly independent vectors does a certain vector space admit. Let's consider a set of linearly independent vectors from I equals 1 to lowercase n, lin indep vectors. And we don't know if this is the full set of linearly independent vectors, but what we can do is we can check vectors from the space and see if they can be written, I'll put a question mark, as a linear combination of these vectors. If all of the vectors that we want to check end up being able to be written in this way, then we would end up saying that this set of vectors does span the space, is a full set of linearly independent vectors. But alternatively, what we could find is that there's a particular vector v that cannot be written as a linear combination over these other vectors. And if that's the case, then we would say that the span of the set does not equal the full vector space capital V. And if that's the case, then we should add that vector V to our collection of vectors. And then the set of vectors will be even fuller. So I'm going to define a vector V sub n plus 1 and set that equal to the vector V. And then our set is going to be, it's going to look very similar, but it's going to have a new member, n plus 1. And then we can check the span of this set and see if it equals the full set of vectors. In other words, we can search for another vector, u, and see if it can be written as a linear combination over this new set of vectors, vi from 1 to n plus 1. And again, if it's not possible to write this equality, then we would just define a new vector vn plus 2 is equal to U. And then we would say that our set is going to be vi from I equals 1 to n plus 2. And then we can continue this on and on until we feel that we've found all of the possible linearly independent vectors that we can find. And when that's the case, if we check any vector in the space W, and let's say that we ended up finding capital N vectors after this whole procedure, we would find that any vector W can be written as a linear combination over the capital N vectors that are linearly independent V sub I. That means that the span of this full set is equal to the full vector space. In other words, the set of all linear combinations of the vectors v sub I from I equals 1 to n is equivalent to the entire vector space. If this is true, then we would say that vi from 1 to n is a basis. So a basis is a complete set or maximal set of linearly independent vectors. In other words, it's a set of vectors that are linearly independent and span the space. And as I already described, the great thing about a basis is that any vector in the space, I explained it here, any vector in the space can be written as a linear combination over the basis vectors. So there's an equivalence between vectors in the space, which I am labeling W here, and a set of coefficients C sub I from I equals 1 to n. The set of coefficients is called a representation. Lastly, the dimension of a vector space, that is the number of basis vectors. In this case, that would be capital N. Coming back to the animation that I showed you in the beginning of the video, I hope now you understand more clearly why the set of linear combinations of these two vectors does not span the entire three-dimensional space. These two vectors are indeed linearly independent, which can be seen because they are pointing in different directions. And when we added together the linear combinations and produced the yellow points, that full set of yellow points gives us an idea of the span of those two vectors. I explained earlier that if n linearly independent vectors span a vector space, then the dimensionality of that vector space is n. Given that the dimensionality of the vector space that I'm showing in the animation is 3, that would mean that it would take 3 linearly independent vectors to span that space. We only had 2, and that explains why those 2 vectors only span a subset of the three-dimensional space and not the whole space. This subset is the set of vectors whose heads point to the plane. I'm not going to get a chance to explain it here, but it actually turns out that this subset of vectors is itself a vector space. It's called a subspace of the original space.